more advanced. Now you get into lenses that can have 4 different curves in one quadrant. I mean, with the machines that we have now, we have the ability to put 4 different base curves inside an optic zone if we want to. When we first got this machine about 15 years ago, it's been a long time, I cut a lens with a square optic zone just to see if I could. So we made a square optic zone on a lens. I explain it, you know how the cars have fancy wheels and they use a CNC machine to cut it out? It's similar to that, is we're punching out these lenses. We're not just turning them on a lathe, okay? So we have multiple zones that can alternate from toric to spherical. And I call them futuristic lenses because they are. And, you know, there is a company, and I'll give them a little credit, is Wave lenses. It's a good system. They can make freeform lenses like what we do. We can make freeform lenses where we're changing the curve every 5 degrees. We have a different curve on some of these corneas. So these are the different type of toric lenses you could have. You could have what I call bi-axis, like a dual axis, CRT if you've heard of that, but it's a dual axis alignment curve. That's the first diagram I showed. And then a bi-axis with toric reverse and alignment curves. Now that's where the reverse curve and the alignment curve are toric. And then we can get into a multi-axis toric treatment zone to where the optic zone can be toric so that you can reduce or eliminate residual astigmatism. So in that case, right, if you had K readings that were 43 over 46 diopters, and you had a cornea that was -3, -5 cylinder, you would have to make the center of the optic zone 2 diopters flatter on the vertical meridian. And that's a little tricky to picture unless you do this all day like I do, right? So the multi-axis, we can reduce residual astigmatism. Now this is basically, we build a corneal model. What we do is I take the topographer data, whether if it's a MedMod, then I take the MXF file and I import it into my software and I have the exact data. Oculus, I have to pull it, simulate the data because I can't get the file. And most of the other topographers will, at the laboratory, will extract the data that we want from the topography, and then we'll build the corneal model of the patient's eye and build the lens on top of that. This is kind of what Oliver was showing earlier. Remember when he showed this drawing? I think he wiped it out. But he was showing the drawing to show E value. And you can see the 0 eccentricity is a sphere, like a ball, a circle, right? 0.3 is a little more elliptical, 0.6, 0.9 is very elliptical, right? So in this case, we're looking at this cornea where we have 4 different quadrants here, where blue is and we're simulating this, but a 44 1/4 with a 0.5E would have a sag height of 1.974, and that would be this meridian here. At axis 90, you'd have a 4675 with a 0.60 at axis 90, and you'd have a 2.81, that's up top. Here we have a 44 1/4, 0.5E, axis 180, 1.974. You can see those two are the same here, right? And then down below, we have a steeper sag, 2.149. So that would be for an inferior steep cornea, if we were going to make that, okay? And that's really just a diagram to grasp the concept of what we're doing. This is a case that you can see, this is a pretty irregular cornea, right? If you look at the quadrants here, you've got this quadrant is very unique. Then you have this quadrant is very unique. And these two are a little more similar, right? But what we came up with for this is you can see K readings are 4162 over 4337. And that's what we're using here, the 4162 and 4337. So at axis 0, which would be here, and everyone understands that if the astigmatism is oblique, then the lens is going to rotate and follow the axis, the oblique axis. So we typically put a black dot at axis 270. So in this case, the black dot should be right here, so that you know that the lens is positioned properly. Then you've got 4162 here with a 0.6e. That's this area. And that's, see how much flatter the peripheral is here? This peripheral cornea is very flat out there. When we look at the scale, that dark blue is 40 diopters. So you're talking 8.44 millimeters. And dropping down into here, look at the red. It's all the way at 4450. So if you look at the difference on this cornea, you're talking 4.5 diopters of variation on the cornea, which is quite a bit. This is again to show the multi-axis, so that we're showing you've got a flat, a steep, medium, and flat. So you can have super steep down here, steeper than these meridians here, but all four quadrants can be different. So this is getting into aspheric toric curves. And this pertains to the OKEX design, which is the myopia management or myopia control design, and the high minus design. So here we're able to use this eccentricity to flatten the astigmatism. So you kind of think that the optic zones are spherical, but they're not, because we're using aspheric curves here to treat the astigmatism, because aspheric curves can flatten the cornea better. They flatten better because they gradually flatten out and apply more pressure. The farther it gets out, the more it applies pressure on the cornea or the tear film. So that's just kind of, it's showing the design. You've got a reverse curve, another reverse curve, an alignment curve, and a peripheral curve. All not really to spec, but and this is we covered this earlier, but I know a lot of you haven't fit Ortho K lenses, so I can't say this enough times about getting good data. And Oliver and TC, I think, did a really good job about talking. You know, we like to use a Q-tip or a cotton swab to hold up the upper lid. So we have the patient blink. I have the patient pull the lower lid down, and a technician or myself can hold up the upper lid. When people have tight lids, I can't tell you how many times I get topography maps that are like this. It's just lid. I can't see the top or the bottom of the cornea, and we're supposed to design a lens from that, right? So it's so important that you get a good round topography map. And if you don't get a round topography map, you have to retrain your technicians, or retrain yourself to do that. The manual refraction. So when you use an auto refractor or an auto refractor after Ortho K, what it does is it picks up the steep reverse zone and it depicts it as astigmatism. So you might get a patient that's seeing 20/15, right? Perfect vision, and your autorefractor says plano -6 because you have a 6 diopter steeper reverse zone where the tissue's built up. So it's very important to me when you follow up with these patients that you do a manual refraction. Do you guys both agree with that? Too? Those? Yeah? And I can't tell you how many doctors send us the autorefractor and they say, they're seeing good, but they have so much astigmatism, you know, so that's another important tip, you know, kind of a pro tip. And then trying to figure out, is it central or limbal astigmatism? And everyone knows the difference between central or limbal astigmatism, right? Pretty much? Yes? So that's important because, you know, when we get customers who want to order a lens over the phone and they give us K readings and they say it's 43, 46, -4, -2, and we have no topography map, we don't know what kind of astigmatism it is. And if it's central astigmatism and we make a limbal astigmatism design, it's going to fit much too tight vertically, way too steep. So those are all very important things that you need to learn. And then really determine the indicated or the best flat axis lens design. And what I mean by that is when you're starting, kind of like what we were doing with Oliver and TC, is we were trying to fit a spherical lens on corneas that needed a toric design, right? So, but first, in my mind, the first thing I do is I look at the horizontal axis and I say, what lens is going to fit there? What lens will fit good horizontally? Then, once I have an idea of what's going to fit there, then I look vertically and say, okay, you almost want to treat it like two corneas. One cornea here, one cornea here. So then you're going to look at that steep meridian and say, hey, it's a 46 with a very low E value, right? Usually when you have limbal astigmatism, it has hardly any eccentricity, usually 0.3 or less. And horizontal is usually 0.4 to 0.7. So does everyone kind of understand that? Looking at the flat axis first. And the critical data for designing manufacturer, is that the same? That's the same slide. What happened there? So this is where we're getting into elevation, where we were talking earlier. We touched on it a little bit, and the elevations that the Pentacam is giving is at an 8 millimeter diameter. So just like E value, most topographers give an 8 millimeter E value. And does anyone know or have an idea of what the chord diameter of a typical Ortho K lens is? Anybody? Typical chord diameter, Joseph? 10-0. So if you had a 10.6 lens, you might have a 9.6 or 10.0 chord. And what I mean by chord diameter is that's the end of the last alignment curve before the peripheral curve. So it's the last place where the lens is not touching the cornea, but at that area. Once it's the peripheral curve, we don't care about the peripheral curve, right? So really, what you have to do is you want to take the chord diameter of your lens, divide that by 2, and that's how many millimeters you should be out on the cornea. So if you have a 10 millimeter chord, you want to check the elevations at 5 millimeters, right? And if you don't have a good topography map, you can't get the elevation at 5 millimeters, especially vertically. That's why it's so important to get the lids open, right, when you get into toric design. And I have to throw out another Medmont topographer is it allows us to get the elevation at any diameter. So I actually have someone in context, when doctors email us the Medmont file, they import it into our Medmont and they pull the exact elevations for me at each quadrant, and then we input that into our software and design the lenses from that. So having that elevation, 8 millimeter elevations and 8 millimeter E values don't mean a lot to an orthokeratologist. Does that make sense? And that, you know, because you're fitting bigger lenses, you really need the real data. And that's what I'm saying. Divide that by 2. 9.6 divided by 2 is 4.8. That's where you want to get your elevations. Measure the height of the flat and steep axis at the end of the cord, and that's what you're doing. You're measuring that elevation. If you're using E value, we basically input the flat K and the flat E value. See how I put flat E value? And to determine the flat axis design, here we have the steep K and the steep E value to determine that steep axis design. So that's where I feel like it's imperative. It's very important that you have a topographer that can give you the eccentricity at the flat, the eccentricity at the steep. And I think that's about the 10th time I've said that today, right? So it is very important. And these are really the topographers that I know of that offer that flat axis is Medmont, Topcon, Oculus, and Keratron, which Keratron's not so popular anymore, but it was a very good topographer in its day. So this is kind of a question here, is what cornea has a higher eccentricity value along the vertical meridian? So up and down here, does this map have a higher eccentricity value, or that map have a higher eccentricity value? Does anybody have their guess? This one? This one? Yeah. This one definitely has a higher eccentricity value here. You can see how this flattens out up here, right? This is central astigmatism. And this is true limbal astigmatism. See how it's steep all the way from the top to the bottom? It's red. So that's when you know you have limbal astigmatism compared to central astigmatism. This cornea, we can fit this a lot of the time with a spherical design. We don't need a toric design for that cornea, but this one, we need to have a toric design. Sometimes a cornea like this, we might put only toric reverse curves. So maybe we have the reverse curve coming around, and here it's, in this quadrant, it's flatter. Here we make it steeper, and then it's flatter again and steeper again. But the alignment curve, you can see that cornea is the same all the way around, right? Over here, it's not. So does everyone understand that? This is kind of elementary, Ortho K 101, right, TC? Central astigmatism, higher E value, lower sag at axis 90. Vertical cornea is symmetric, so toric alignment curves, not always necessary. And then I do say half or 1 diopter toricity can work there very good. And that's showing basically just a couple central astigmatism maps. This is the limbal astigmatism, E value greater, so your E value lower, so you're going to need the toric alignment curves on that cornea. So determining elevations. Now this is TC and Oliver were starting to talk about elevations, and elevations are a great tool for evaluating. You as a doctor can look at the elevation and say, oh, I'm sorry. You can look at the elevation and say, I got big changes right there. I think I'm going to need a toric, right? You think you're going to need a toric over here, and that's this cornea, that map, but that's the elevation map for that eye. And you look at that, and you definitely want a toric for that, right? So once you figure out those elevations, then again, you're going to grab that core diameter, and I'm even showing you for the E system, with a 10.6 diameter, you're going to have a 9.6, so you need a 4.8 millimeter elevation to fit it custom, scientifically, right, mathematically. With the EX, it's a 10 millimeter, so you got to get your elevations all the way out to 5 millimeters here, 5 millimeters there, 5 millimeters here, and 5 millimeters here. And then we can build the perfect model of your patient's cornea to build the perfect lens on top of the perfect model. That's the science part of this. Determine those elevations. So here we have 58 microns of deviation. That's a lot. That's 3 diopters of deviation. Down at the bottom, it's 33. And most corneas have the greater deviation down here, right? Most corneas have inferior steep areas, not superior steep. These types of corneas, where the top is steeper, they're kind of my nemesis. They're very tough to fit because if you put a steeper alignment curve up here, gravity wants to make the lens rotate down. And then you'll have the steeper one down here and the flatter one up there. So they're tough to locate, these lenses. And here again, looking at these elevations, we have 51 microns. That's 2.5 diopters of flattening right there. And then 30 microns on this side. So, which is basically 1.5 diopters. So if you think of a diopter as being about 20 microns, 2.5, this is 50 microns. 2.5, that's a lot of flattening going on there. So any deviation, I say greater than 40. Some people say 20, 30. It really depends on if you have diagnostic lenses and you put the lens on and you see the lens rocking because of the astigmatism, that tells you you need a toric design. It's just a matter of how much toricity you need. The other thing also that you have to keep in mind is as you fit the lens bigger, like we're talking about the 11.4 diameter lenses compared to 10.6, the farther you go out, the bigger the deviation is. The more it flattens. So if I'm fitting an 11.4 and my core diameter is a 10.6 millimeter, that 10.6 is really flat out there. Now that's one of the reasons why I'm not the biggest fan of fitting by HVID all the time. I don't think you always need HVID. When you have a lens that laterally displaces, up and down is easy to fix. Righty high, righty low, I believe you can fix that easy. But when a lens goes temporal or nasal, that's when it's harder to fit. That's when sometimes I've tried to fit the perfect lens and tight lids will drive the lens nasal. Even if the lens, without the lens looks perfect. But once the lid gets involved and they blink, it starts forcing it nasal. And when they sleep with tight lids, it'll actually position nasal. So that's just my take on that. And everyone gets, the E-system, once you start to use the E-system, it's very easy. 0.05 E equals 10 microns. 0.1 E equals 20 microns. So when you think of a 0.2 E change, that's going to be a 40 micron change. And we rarely loosen or tighten the lens by more than 20 microns. If we have a lens, we design the lens and a doctor sends us the map, we get the video, we look at it, rarely do we loosen it or tighten it by more than 20 microns. So 0.05 E, 10 microns is sometimes all you have to change the lens to get it to fit better and perform better. So using specific elevations for corneal height, I think that's similar to the other slide. This is at a 9.2 chord for a 10-0 lens. Just a little variation from what we were looking at. This is where we're getting into. This will be a little more complicated, a little more complex because you're looking at a case here that's 43 over 46, -4, -3 at 180. We're saying it has a 0.5 E eccentricity, and what we say, because of the 600 corneas that we analyzed to come up with a 0.52 eccentricity on average, is if you don't have an E value, start with 0.5. We found 0.5 E works for 85% of the corneas. The other 15%, they're odd people. Odd corneas. So that's the 0.5 E. So the horizontal lens design here would be a 43 -4, 0.5 E. Now looking at the vertical here, you're going to take the vertical lens design and you're going to take that steep K of 46. So you're going to take the refraction, the spherical refraction of -4, plus the diopters of corneal cylinder. not the refractive cylinder, but the corneal cylinder, right? So if they have -4 refractive cylinder and only -3 corneal cylinder, you have to use the corneal cylinder to get the lens to fit correctly. So in this case, it's going to be 4 plus 3 diopters of corneal astigmatism. So the target power for the vertical meridian is a -7, right? Or -4, -3 is basically how we write the design. But the target power, the lens design vertically would be a 46 -7, and here it's a 43 -4. And that should be pretty simple, I think, for everybody to get, right? So this is again getting a little kind of complex, but you know, we're looking at central versus limbal astigmatism designs. So if I had a cornea that's central astigmatism, like we talked about, versus limbal astigmatism, you can see that both the base curves are all 882 here. 43 -4, 46 -7. We got the 882, but look at the 0 and 180. Because the 180 was symmetric across. You've got a 702 reverse curve, a 788 alignment curve, and the peripheral curves are kind of fake because in context, we use an aspheric peripheral curve. We do not use spherical peripheral curves. We don't use an 11, we don't use a 1050. We use a 10 or a 1050 with a 2.0 eccentricity, where we're kicking it up at the end like the tip of a snow ski. Right? Then you look at the 90 axis, you've got a 608, right? Because the 90 was steeper, right? Remember up top, it was steeper, it was steeper up top on the map. So we've got a 608 there with a 733 alignment curve, but then when we go down to, look at, that's a mistake in that should say axis 270. So I've done this presentation a lot, and I've never noticed that, so I'm going to fix that. But at axis 270 here, for central astigmatism, you're going to have a much flatter alignment curve for central astigmatism. You see that? Flatter reverse curve, flatter alignment curve, because you have limbal astigmatism versus central astigmatism. Does that make sense to everybody? Okay. And you're calculating a corneal model for basically each axis. And this is getting into, now we're talking about a quad symmetric lens. So this lens here, every 90 degrees, the lens is changing. So this is 4 lens designs in one contact lens, right? Base curve is all 882 though. But look at the reverse curve at axis 0 is set 14, and at 180, 702, a little steeper, because we have that 0.6E, we need a flatter alignment curve here, right? And then we got a 0.5E at 180, it's about a half diopter steeper, right? And remember how we said that 0.1E equals 20 microns, which is about a half diopter. So that's the 0.5 to 0.6. Then when we get into the 90 and 270, you can see that look at the reverse curve on the 270, 596, and that's something that I don't like to go steeper than 6 millimeters on the reverse curves, because when they get too steep, they tend to pinch the cornea a little bit. They just pinch. Somehow they're not comfortable. Even if you flatten the alignment a little, sometimes those steep radius in the reverse curve can cause comfort issues. But does that illustrate a quad symmetric lens for everybody pretty good? And then picture that lens, and what we're doing is we're blending those zones. So imagine if this is 90 degrees, right? At the 45 degree mark, we're going to be right in between the two of the axes. So from 0, if this is 0 and this is 270, so if you look at a 714, it's going to go from 714 down to 596 at the bottom. So it's going to gradually go from 714 to 596. So right in the middle of there is what? 1.2 millimeter radius change, which is quite a bit. And when we're changing radius like that, a lens like this can take us 3 minutes to cut. And a spherical lens, we can cut it in 40 seconds. So that's why we charge more for the toric lenses. Okay? So, this is just showing that the lens should fit like a normal reverse geometry. So this is the same cornea, the same eye, and you can see the cornea there, it's the same eye. And this is the toric lens on there. See the black dot right there? I don't know, I don't think that's the black dot actually. But this is a spherical lens. So you can see the same cornea, it should look like a spherical lens. Once you have a toric cornea on there, it should look like a spherical lens. With toric lenses, the hardest thing to figure out when they don't work properly, it's hard to figure out what axis is the problem, right? And I personally find that the steep meridian is usually the culprit. I don't know if you find that when you design your torics or not, but when you look at this pattern here, that's sealed off pretty good, right? That's sealed off, it's very even all the way around, but it does look a little darker down here, right? So if I saw that on the fluorescein pattern and the patient wasn't getting the perfect map, then I would flatten that curve just a little bit. And I might flatten it up top, raise the E value at both quadrants. And then it's okay to have, I call them healthy lenses. To me, if I have a little bit of edge lift down here, this is obviously too much, right? But if you have a little, what I call a lens breakaway, if it breaks away a little on the blink, then it's exchanging oxygen. It's bringing oxygen and fresh tears into the cornea. So I just don't like tight lenses, and I'd rather see a little bit of fluorescein lifted off. Okay, so anybody, I didn't even read that, but always evaluate the horizontal meridian first. So you want to look at this meridian first, then analyze your steep meridian. So here, when we look at this fit right here, it looks pretty good, right? But then when you analyze this, you know that's not good. Here, it looks good all the way across, okay? Once you're satisfied with the horizontal fit, then evaluate that vertical fit. I kind of already covered that. You can see this has some breakaway up top. Probably need to be tightened. That lens actually looks a little too big for that cornea, personally. But the 12 to 6 reverse zone, that's something that's very important. And this is a detail again. Small details matter when you're doing fluorescein evaluation. See how much more fluorescein is here and there than here? See the vertical meridian? Because it's so much steeper, and you're trying to flatten that center, and because it's steep, it's gonna have more tear film in there, right? It's got a deeper tear layer. So once that cornea molds all the way, then it typically will even out. But does that make sense to everyone? Okay, so here's the toric alignment zone design. These are I don't know, are these Humphrey maps, I think? These are some pretty old. Look at the date on that. I wish I was back in 2004. So that's how long we've been doing toric lenses. Over 20 years we've been doing these. And this is central astigmatism, right? Central astigmatism. So all we need is toric alignment zones on this. We don't need toric reverse curves and that. Toric reverse and alignment curves. This is getting into the fancy lens. I mean, this case was one of our patients back when. He's actually a pilot. He flies. Everybody knows UFC. You might know UFC. Dana, the guy that owns that, he's his personal pilot. So he needs to see, right? So we fit him in. We did Ortho K on him, and I don't see a lot of patients anymore, but he's one of my favorite patients. So I still see this patient. But the toric reverse alignment curves, they really contour the whole cornea. And then this is toric treatment zones. So this is getting into residual astigmatism. So if you have that patient that's 42 to 44 K readings, that's 2 doctors corneal still. But if they're -3, you're not going to be able to get rid of all that refractive cylinder. So we use toric treatment zones, and you can see that we're almost inducing that steep area. You see that? We're doing that on purpose. So here it's smooth, right? It's symmetric. Then that's during the molding process, and once that patient was done and completed, you can see the astigmatism that's in there. That's from the toric treatment zone. And that's more examples, not specific cases, right? They're specific, but I'm not going through every number and detail, but going through the general theory on toric lenses, and so when do you need that toric lens? We've said 20, 30 to 40 microns. And then you as a doctor, it's up to you. When you put a spherical lens on and you see that tilting, then you know you need a toric right there. And sometimes, about 10 or 15 years ago, I was doing a lecture, I don't know, Vision by Design in the US or something. And I said, someday every Ortho K lens is going to be toric. And it's almost gotten to where most lenses are toric. They really, you get a -3 sphere, and the biggest problem is you can have a symmetric cornea in the middle, it's perfect in the middle, symmetric, but if they have peripheral astigmatism like this, and let's say this is spherical, they're a -3 sphere, you fit them, it looks good, you got your alignment, and what a lot of doctors do that I disagree with is they'll fit on mean K. So if you have a 43 and 45, they'll fit a 44. And they'll fit on mean K. And what that does is it makes this meridian, the horizontal meridian, is much too tight. Much too tight. And then the vertical meridian is still too flat, too loose. So the mean K fitting, and there's a very good lens design, actually. Arthur Tung's lens, the GOP lens, he fits mean K a lot, and his lenses work well. They do fit tighter than I like the lens to fit, but his mean K lenses, they work, so I can't criticize it, but I personally don't think that's the way to fit these patients. I think you're better off using an actual toric design. With all of that said, does anyone have any specific questions?